In this video, we learn what scalars and vectors are, and we practice using them in 4 important physical laws and concepts so that we learn how we can relate these quantities to the world around us. First, let's define scalar and vector quantities. Scalars are physical quantities that only have magnitude. Each quantity in physics is shown by a symbol and has a unit to give meaning to the magnitude. For example, temperature can be represented by T or theta and is measured in Kelvin, Celsius, or Fahrenheit. Time, mass, distance, speed, density, electric charge, and energy are some other important scalars. On the other hand, to represent a vector, we need a magnitude and a direction. In physics, they are usually used in componential form, consisting 3 unit vectors I, j, and k that are orthogonal and 3 components of magnitude along x, y, and z axes. The magnitude of a vector can be calculated by the square root of the sum of the components squared. Similarly, each vector quantity can be shown by a symbol and a unit, which is the unit of its components. For example, the velocity of a particle or an object is a vector quantity. Other examples of vector quantities are position, force, acceleration, momentum, electric field, and so on. Now it's time to explore how we can use these quantities to talk about physical laws. Our first example is the famous Newton's second law. It states that if we have an object with mass m and exert a force in this direction, it will gain an acceleration in the same direction. So if we have a 2 kilogram object moving in this direction and constantly increasing its velocity in the same direction, 2 meters per second each second, we know that a force is increasing its velocity in this direction. Now consider the same object moving in the same direction, but this time with a decreasing velocity. It suggests that the acceleration is in the opposite direction, and a force twice the size of the acceleration is acting on the object to stop it or change its direction. Our next example is the law of universal gravitation. Suppose that we have 2 masses m1 and m2 separated by a distance r, in which r is a scalar. The gravitational force between the 2 masses can be calculated by this formula. If we take r hat to be the unit vector in this direction, which is usually used in spherical coordinates, the force that the second body exerts on the first one is F21, and the force that the first mass exerts on the second is F12, which is in the opposite direction. This symbol here is called the gravitational constant, which is one of the many invariant quantities that we come across in physics. By a quick dimensional analysis, you can find its dimension to be Newton meters squared over kilograms squared. The magnitude of this constant is 6.67 times 10 to the power of minus 11 Newton meters squared kilograms squared, or purely in SI units, meters cubed over kilogram seconds squared. The next example is a scalar, kinetic energy. Consider an object with mass m that is moving with a speed v. We know that v is a vector, but its speed is the magnitude of v, which is a scalar. So the kinetic energy can be written as half of the mass times the speed squared. You might ask where this constant comes from. Suppose that the object moves from this position to this position with the initial velocity of v and the final velocity of 0, which means it stops. So there must have been a force acting on the object in opposite direction to stop it. And the work done on the object by an agent is the dot product of the force and displacement vectors, which is minus Fd. Negative work means the kinetic energy of the object has been transferred from the particle. Now, using Newton's second law and this equation that we'll be talking about in other videos, and also work energy theorem, we can see where the 1/2 constant come from. We'll be talking about them all in more detail soon. Our last example is Hooke's law. Suppose that we have a body attached to a spring. When the spring is not stretched or compressed, it is in equilibrium. When the spring is compressed and its length changes by an amount x from its equilibrium position, a force in the opposite direction is exerted on the object by the spring, trying to take it back to the equilibrium position. Similarly, if we stretch the spring, the same force acts on the object, but this time in the opposite direction. And finally, K is the spring constant and shows the stiffness of the spring. The higher this constant, the bigger force will be, and the spring has more tendency to go back to equilibrium. To calculate this constant, we can hang an object from an almost massless spring, find the displacement from equilibrium or change in the length of spring, and find the force by the fact that the force exerted on the object from the spring is equal to the force that wants to pull the object to the ground. And as the object is not moving, we can say that F is equal to mg, the gravitational force. So the spring constant can be calculated by dividing the force, the spring force, by the change in the spring's length. Pay attention that this constant is a positive quantity, so we use the magnitudes.